Hello, can you hear me? I think you can. Hi, everybody. So today, going to talk about some new reactions. I'm not going to talk about exam number 2 anymore. I had a review on Friday, and we got to move on, push on to new material. Okay, so what's going on in the lecture right now is a whole lot of talk about the enolate and about the various enolate reactions. So that's what I'm going to talk about in today's discussion. All right, so there are actually 4 important enolate reactions, but Professor Porco has only gotten to 3 of them so far, and that is alkylation of an enolate, aldol reaction, and the Claisen reaction. So that's what I'd like to talk about today. These are, all of these reactions are founded on the creation of an enolate. So let's just review and talk about that for a minute. The enolate. So what we're looking at here is a carbonyl compound where the carbon next to the carbonyl carbon, this is called the alpha carbon, carbon next to the alpha carbon has a proton on it. And this proton is moderately acidic and it can be removed by a base. So a base comes in, removes the proton, which is bonded to the alpha carbon. Remember, the alpha carbon is the carbon next to the carbonyl carbon. And so the base has removed the proton. And what we're left with is a dot minus on the alpha carbon. Okay, this is the enolate. The enolate anion. It's a nucleophile. All right, now this the enolate actually has 2 resonance forms. The one I've drawn here is the one that for me makes most sense in trying to predict what the enolate is going to do. However, this has a second resonance structure that puts the negative charge on the oxygen atom. Technically, this is the better resonance form. Mostly because the oxygen is electronegative, and this resonance form puts the negative charge on the more electronegative oxygen rather than here on the less electronegative carbon. And Professor Porco nearly always prefers this resonance form. I have problems with this resonance form because the reactions of the enolate are best understood by considering this resonance form that has the dot minus on the alpha carbon rather than this one. But technically, this one is the better of the 2 resonance forms. Okay, so that's what an enolate is. The choice of base can be critical. So it's not just in many of these reactions, particularly in the Claisen, the choice of base, it can't just be just anything. But let's just keep everything nice and generic for now. Okay, so this is the enolate. It's a nucleophile. It's going to react with various electrophiles. And as I said before, there are 4 important enolate reactions. We can only talk about 3 of them today, but that's a whole lot of stuff because the reactions of the enolate are some of the most difficult in organic chemistry. Okay, so first up, first of the 4 reactions, alkylation of an enolate. So we have a carbonyl compound that has a proton on the alpha carbon. And so the alpha carbon will now be removed by some kind of base. H base is produced, that's the conjugate acid of whatever base was used. And we get this dot dot minus on the alpha carbon, and that will be our nucleophile, that's our enolate. Now, for what follows, I'm always going to put a little star on what used to be the alpha carbon. So that's going to be, that's the attacking nucleophile. In the alkylation of the enolate, this nucleophile now engages in an SN2 reaction in which it's going to displace one of our familiar leaving groups, like a halide or a tosylate. So in our second step, we react the enolate with something that has a leaving group. So I'm going to put an R there, and R can be, as I said, a halide or a tosylate. There are restrictions on what this can be. It has to be either primary or secondary, and it can never be a tertiary substrate, because this is an SN2 reaction, and we never see an SN2 reaction on a tertiary substrate. Okay, so what happens in SN2 is that the leaving group goes away and the nucleophile takes its place. All right, I'm going to put a dot on the electrophilic carbon. So the star is the nucleophile, the dot is the electrophile, and the nucleophile replaces the leaving group in the substrate. Okay, so see how I hooked up the star and the dot. I hooked up the star and the dot, and the nucleophile, the star, is where the leaving group used to be. This is just what happens in an SN2 reaction. All right, and so there's our product of alkylation of an enolate. And the overall effect here has been chain extension at the alpha carbon. So there's a new organic group there that wasn't there before on the alpha carbon. So the purpose of alkylation of an enolate is this chain extension at the alpha carbon. All right, so I kept everything very general here. Now let's do a specific reaction. Okay, so let's predict the product here. All right, it's the alkylation of an enolate recipe, because I have a carbonyl compound that has an alpha carbon, and there are alpha protons on this alpha carbon. They can be removed by a base. So that's my star, that's my nucleophile. This other guy over here, that's my electrophile. I see a leaving group on a primary or secondary carbon. And so the star and the dot are going to hook up, and the overall result is going to be, I'm going to extend the chain of carbon atoms here at the alpha carbon. All right, so before we draw the structure of the product here, let me just point out, as I said before, the choice of base is critical. We know that OH minus, for example, is a base, but we wouldn't want to use OH minus here. Why not? Right? Why can't we use OH minus here? OH minus is a base. It would be the absolutely worst thing to use. Why is that? Are you thinking? Anybody have a suggestion? Why no OH minus? The reason for that is that this is an acyl derivative. It's a carbonyl carbon that's bonded to something that's not carbon and not hydrogen. So if I use OH minus, I'm not going to get alkylation of the enolate. I'm going to get saponification of the ester. I'm going to get an acyl substitution where this OET will be replaced by OH. And since it's basic conditions, it will actually be a carboxylate. All right, so notice that when I'm using this ester, the esteratic portion of this ester matches this base, so that if I get acyl substitution, if this thing that is not carbon and not hydrogen breaks off from the carbonyl carbon in an acyl substitution reaction, the product is going to be the same as the starting material. So no mu compound will be created. Like I said before, the choice of base can sometimes be critical. OH minus is a base, would be exactly the worst thing you could do here. All right, so let's draw the structure of the product. I'm hooking up the star and the dot. I'm hooking up the star and the dot. The nucleophile, the star, is where the leaving group used to be, so that will be the structure of the product. Okay, so how'd that go? All right, so let's try another one. Okay, so how about you draw the structure of the product here? What are we talking about? Alkylation of an enolate. You're looking for a proton on an alpha carbon. What's that? That's the carbon that is next to the carbonyl carbon. You're looking for an alpha proton that is removed by the base. In this case, I'm using this lithium diisopropylamide. That is a powerful non-nucleophilic base because it's sterically hindered. And then I'm also looking for a leaving group. Well, I see the leaving group there. That's the Br. Draw the structure of the product. Find the star, find the dot, hook them up. So my star will be here. That's my nucleophile. The LPA came in and removed an alpha proton that was there. Notice this is also an alpha carbon, but there are no protons there, so the star could never be there. And here's the dot. That's the electrophile. And now I'm going to hook up my star and my dot. But what I notice in this problem is when I hook up the star and the dot, I'm going to get a 6-membered ring. So this would be an example of an intramolecular alkylation of an enolate, where the star and the dot, where the nucleophile and the electrophile are the same molecule, and I can get a nice thermodynamically stable 6-membered ring. All right, so hooking up the star and the dot. Here's the star. I hooked it up with the dot. Okay, star, carbonyl, a carbon atom with 2 methyl groups on it, and then 3 CH2s, 2 CH2s, and then I arrive at my dot, 2 CH2s, and then I arrive at my dot. So that would be the product of this intramolecular alkylation of this enolate. Okay, so that's alkylation of an enolate. It's not too complicated. It's SN2. You're looking for the nucleophile, the star, on an alpha carbon. You're looking for something that has a leaving group. The dot has a bromide or chloride or iodide or tosylate or something like that. on them. Okay, so that's alkylation of an enolate. Now let's go on to our next reaction. But before we do that, how about let's try a synthesis problem that uses alkylation of an enolate. What about trying to make all right, so now this is a very strange synthesis problem, and we'll see as we develop the synthesis of this compound. This is one of the great exclamation points in organic chemistry. You'd never think that this reaction would work, but it does. Okay, so I'm looking at this thing, right? This is a synthesis problem. I'm looking at this thing and I see, oh, this is the product of an alkylation of an enolate, because this is the alpha carbon, that's an alpha carbon there, and I can interpret this four-membered ring as the chain extension at the alpha carbon. So this thing could be made in the following way. My starting materials would be that, plus, to make this four-membered ring here, maybe a Br there, and then another Br there. Okay, so this is my strategy. That's my strategy. That's not my synthesis. I'm just figuring out how I'm going to put this molecule together. Okay, so now I'm ready to write out my synthesis. So starting with this guy here, what I see is that this is an alpha carbon. What's an alpha carbon? It's a carbon next to a carbonyl carbon. This is an alpha carbon. It's a carbon next to a carbonyl carbon. And this is an alpha carbon. It's a carbonyl next to it's a carbon next to a carbonyl carbon. So this molecule has 3 alpha carbons. How does this molecule know that I want enolization here and not here and not here? Well, the way this molecule knows is because this guy here, that's where my star is going to be, that is bis alpha. It is alpha to 2 carbonyl groups. It's much more acidic, by about 8 orders of magnitude more acidic than a proton that is next to just 1 carbonyl. So this proton here, its pKa is about 20. This proton here, its pKa is about 20. But when an alpha carbon is sandwiched in between 2 carbonyls, that's much more acidic. This proton here, his pKa is about 10. So when you have a molecule that has a carbonyl sandwich, where a carbon is sandwiched in between 2 carbonyls, those are the most enolizable, those are the most acidic type of alpha protons, so that there is no question of where the enolization will happen. It's going to happen here. Okay, so now I need to add some kind of base to this. What would be a good base to add? Hydroxide is good enough, because hydroxide is a powerful enough base. The conjugate acid of water, the pKa of water, which is the conjugate acid of OH minus, is about 16. So that's plenty good to enolize this position. Okay, so I'm going to add OH minus. That's going to be my first step. it's going to enolize that bis alpha position. It's going to enolize the star. It's going to enolize the carbon that is trapped between the two carbonyls. There's my dot dot minus. That's my enolate. Okay, and again, one of the reasons why the bis alpha position is so acidic is because it's much more resonance stabilized. So I could write a resonance structure, right? I could write a resonance structure where I'm resonating that negative charge to the left, and I could write a resonance structure where I'm resonating that negative charge to the right. And so this enolate has these two additional resonance structures that stabilize the enolate, whereas if the carbon atom were only next to one carbonyl, there would be fewer resonance forms. That's why it's not as acidic. Okay, so now I'm ready to do my alkylation using this compound. All right, so there's my star. Here's my dot. The star and the dot are going to hook up. Try to crowd it in here. There's my star. There's my dot. They hooked up. Okay, so now I need to enolize this a second time because all of the enolate has been consumed in this reaction. There's no more enolate left. It has all reacted with the with this 1,3-dibromopropane to give this. So now I have to enolize this again. I could use more OH minus. That's going to give me a new enolate here, and then that is going to displace this bromide, and that will be my target molecule. 1, 2, 3, 4. So ordinarily, we don't think that 3-membered rings and 4-membered rings are favorable, but believe it or not, this reaction works. You get about 60% yield of this product. This is one of the big exclamation points in organic chemistry, that this alkylation actually will work. Okay, so the synthesis was 3 steps. First step, enolization, right? The equilibrium constant for this reaction is about 10 to the 7. In other words, that when I treat this compound with the hydroxide, it's 100% yield of enolate. It's all been converted. Starting material has all been converted to enolate. There is no OH minus left. It's all been all underwent protonation in this acid-base reaction to become a molecule of water. That's why I have to re-enolize. That's why I have to have more hydroxide in the second step. Okay. So now let's go on to our next reaction. And our next enolate reaction is the aldol. All right, so once again, we start with a carbonyl compound that has an alpha proton on it. And in the aldol reaction, This starting compound here is nearly always going to be, it can be a lot of stuff, but it's usually going to be an aldehyde or a ketone. It could be other stuff, but it's nearly always going to be an aldehyde or a ketone. That's going to be my nucleophile. And so I add base to this. For an aldol reaction, hydroxide, methoxide, or ethoxide are good enough. Add hydroxide. And so this is going to deprotonate the alpha carbon. We get a dot minus on the alpha carbon. That's my nucleophile, that's my star. Okay, now the equilibrium constant for this reaction is small, because the pKa of an aldehyde or a ketone alpha proton is about 20. The pKa of water is about 16. The equilibrium constant for this reaction is about 10 to the minus 3. That means that at equilibrium, there is tons of aldehyde or ketone unenolized left, right? And there's tons of hydroxide left, so that this small equilibrium constant is telling you that. Okay, so now that's my nucleophile. Now it's time to feed this thing the electrophile. And in the aldol reaction, the electrophile is nearly always, it could be a lot of stuff, but it's nearly always going to be a second aldehyde or ketone. So here's my dot coming up. Here's my electrophile coming up. Nearly always going to be a second aldehyde or ketone. And we've known for a long time that the carbonyl carbon of an aldehyde or ketone is an electrophile. So this is going to be a second aldehyde or ketone. And the nucleophile attacks the electrophile. The dot and the star hook up. And that O minus is now put out by the water that was produced in this first step. So water comes in, functioning as an acid. Hydroxide is produced, and so I get this material here. All right, this is called a beta hydroxycarbonyl. Beta hydroxycarbonyl compound. There's the carbonyl carbon, there's the alpha carbon. The carbon next to the alpha carbon is the beta carbon. So that's why this is called beta hydroxycarbonyl. And another word, another name for this intermediate is an aldol. So that's where this reaction gets its name, is that the product of this aldol reaction is this beta hydroxycarbonyl, which is also called an aldol. Lots of times, this is not what we're looking for in an aldol reaction. Yes, this forms, but most of the time, this is not the product that we're looking for. What usually happens is that the beta hydroxycarbonyl is now heated, and it undergoes a dehydration to form an alpha beta unsaturated carbonyl compound. This loses water to become an alpha beta hydroxycarbonyl. This is called an alpha beta unsaturated carbonyl. This guy, this is usually what we're going for when we do an aldol reaction. All right, so what about this terminology? alpha, beta, unsaturated. Unsaturated means a double bond between alpha and beta, and then it's a carbonyl compound. Okay, so notice that the alpha carbon of the alpha, beta, and saturated carbonyl, follow it back, trace it back, trace it back, trace it back. That used to be the alpha carbon of the starting aldehyde or ketone. And the beta carbon of the alpha, beta, and saturated carbonyl, the dot, trace him back, trace him back, trace him back, trace him back, trace him. Oh, that was the carbonyl carbon of the second aldehyde or ketone. All right, so this is the aldol. This is really the aldol reaction here, but then we usually have this aldol dehydration leading to this alpha, beta, unsaturated carbonyl. Okay, so we'll leave that up there. Let's try to crowd this as much as we can, I guess. How about let's do a product prediction? OH minus and heat. Draw the structure of the product. It's an aldol. It's the aldol recipe. I see an aldehyde or ketone that can enolize, and then I see a second aldehyde or ketone, right? Find the star, find the dot, hook them up. Okay, there's an alpha carbon that has a proton on it. That can be enolized there. All right, that's my star. There's my dot. This is the second aldehyde or ketone. Notice that this guy here can't enolize. It must be the electrophile. It must be the dot, because this molecule doesn't have a proton on any alpha carbon. So it's clear who the nucleophile will be and who the electrophile will be. So the product here is going to be, I'm hooking up the star and the dot, and I'm putting in a new double bond in between because I heated the reaction mixture. So this reaction would go through this scheme of reactions, but the final product here is going to be this alpha beta unsaturated carbonyl. Okay. So let's try some more product predictions. All right, let's try to draw the structure of the product here. You know, actually, I would probably have water in here as well. Okay, so draw the structure of the product here. You're recognizing this is an aldol, right? It's an aldehyde or a ketone that can enolize. Then it's a second aldehyde or ketone. Find the star, find the dot, hook them up with a new double bond in between. All right, so I'm going to be shopping around now for an alpha carbon. What's an alpha carbon? An alpha carbon is a carbon next to a carbonyl carbon. That's an alpha carbon, that's an alpha carbon, that's an alpha carbon, that's an alpha carbon, that's an alpha carbon. Have all sorts of alpha carbons in here. But there is no question of which alpha carbon will undergo enolization. This alpha carbon doesn't have any protons on it, it can't enolize. This alpha carbon doesn't have any protons on it, it can't enolize. So that has alpha protons, that has alpha protons, and that has alpha protons. But we said before that alpha carbon that is sandwiched in between two carbonyls is much more acidic than an alpha proton that is next to just one carbonyl. So in this example, there is no question of where the star will be. There's no question of where the nucleophile will be. It will be there. That's just much more acidic and much more easily enolized than any other kind of alpha carbon. There's my star, there's my dot. I'm going to hook them up with a new double bond in between. There's my star, there's my dot. I hook them up with a new double bond in between. Okay, so how's that going so far? Good, I hope. All right, let's try another product prediction with the aldol. Maybe potassium hydroxide, water, and heat. All right, so what do we get now? Draw the structure of the product. Oh, this one's a toughie. It's the recipe for the aldol. I see an aldehyde or a ketone that can enolize, and I see a second aldehyde or ketone. I'm going to find the star, I'm going to find the dot, I'm going to hook them up with a new double bond in between. All right, so that's an alpha carbon here, that's an alpha carbon there, that's an alpha carbon there, that's an alpha carbon there. It may be kind of difficult because of the way I've drawn this to appreciate the symmetry of this molecule, but maybe if you know about the C2 axis of rotation, C2 axis of symmetry, these two carbonyls are equivalent. So do I enolize here and attack here? Yeah, I could. I'm going to get a 1, 2, 3, 4, 5 member ring. Could I enolize here and attack there? I could. Do I enolize there and attack there? I could. So because it's hard to tell from the way I've drawn this, but actually all of these alpha carbons are all equivalent. So which one is the star? Take your pick. It could be this one. Which one is the dot? It's going to be this other, it's going to be this carbonyl carbon. And so now I hook up the star and the dot, put in a new double bond in between. So a hideously ugly drawing of the product would look maybe something like this. Right, there's my star, there's my dot, new double bond in between, hideously ugly. How about let's fix this? I see a 1, 2, 3, 4, 5 member ring here, a 1, 2, 3, 4, 5, 6, 7 member ring over here. So this could also be drawn a little bit prettier. Looking something like that. So that would be the product of this reaction. Mu double bond in between the star and the dot. So this is an intramolecular aldol. The star and the dot, the nucleophile and the electrophile are on the same molecule, and I saw the possibility of forming this 5-membered ring here, and those are pretty nice, thermodynamically stable. So this seems pretty reasonable. Okay, how about let's try a synthesis problem using the aldol. All right, so there's my target molecule. How could I make that using an aldol reaction? So remember, the product of the aldol is a beta hydroxycarbonyl, but if I heat that beta hydroxycarbonyl, it's going to go on to form the alpha beta unsaturated carbonyl, which is exactly what this is. Alpha beta unsaturated carbonyl on the left and on the right. The alpha carbon, that was my attacking nucleophile. The beta carbon used to be a carbonyl carbon, and that was the electrophile. The alpha carbon, that was my attacking nucleophile, and the beta carbon of this alpha beta unsaturated carbonyl, that used to be a carbonyl carbon, and that functioned as the electrophile. So I could make this molecule one-pot synthesis, OH minus, H2O, and heat. And what would be the required starting material? There's my star. There's my dot. It used to be a carbonyl carbon. In this case, it used to be an aldehyde. They got together, formed that double bond. And on this side, there's my star, and there's my dot. That used to be a carbonyl carbon. So as crazy as it may seem, this reaction works very well. Mostly because I'm getting these 6-membered rings here. And so that plus this, it cyclizes in this intramolecular reaction on the left and on the right. Okay, so let's see. Let's try another synthesis problem. What about if I wanted to make this guy? Okay, what about a synthesis for this thing? What would be our starting materials? It's an alpha beta unsaturated carbonyl. It's an alpha beta unsaturated carbonyl on the left and on the right. And I see I got this 5-membered ring, so it's going to be some kind of intramolecular reaction. The alpha carbon, that was my star. The alpha carbons, those were my nucleophiles. That's what got enolized. And my beta carbons of the alpha beta unsaturated carbonyl, those were my dots. They used to be carbonyl carbons that function as the electrophile. So there are my dots. So It's this plus this, and maybe KOH, water, and heat to promote that dehydration. So notice this guy, it's symmetrical, so which one gets enolized first doesn't matter. Notice this guy cannot enolize. So there is no question of where the stars will be. There is no question of where the, which species will function as the nucleophile, because this guy over here doesn't have any alpha protons. It can't enolize. It must function as the electrophile. Okay. Third and last. Claisen. The Claisen reaction. All right, so this is an acyl substitution that uses an enolate as a nucleophile. All right, so we need something that will furnish the nucleophile. We need something that will furnish the enolate. And it doesn't have to be, but most of the time, nearly all the time, the enolate in the Claisen is going to be an ester. But hold on, there's restrictions on what this ester can be. It must have at least 2 alpha hydrogens. So there have to be at least 2 alpha hydrogens there. So an ester like this, an ester that looks like this, yeah, that's an ester, but there's only 1 alpha proton there. No good for Claisen. Okay, so the nucleophile in the Claisen is nearly always going to be an ester, but there must be at least 2 alpha protons on the alpha carbon. So there's my alpha carbon. Now I'm going to enolize it. That's going to be my star. And in the Claisen, it's very important to match up the esteratic portion of the ester to the base. So if I use OMe here, what's the right base to use? MEO minus. If I use ETO here, what's the right base to use here? ETO minus. So this guy here and this guy here, they have to match up. And the reason for that is because I don't want an acyl substitution. I can't use hydroxide here because that's going to saponify this ester. Okay, so so that the Claisen doesn't get derailed. So the base comes in, it enolizes the ester. I get a dot dot minus here. That's my star, that's my nucleophile. The equilibrium constant for this reaction is also very small. The equilibrium constant here is going to be about 10 to the minus 7, meaning there's a ton of unenolized ester left. Okay, so there's my nucleophile, there's my star. Now it's time to interact this with the dot, with the electrophile. And in the Claisen, the electrophile is nearly always going to be a second ester. It's nearly always going to be a second ester, which could be the same as the first ester, or it could be different. All right, so now the Claisen reaction is an acyl substitution using an enolate as a nucleophile. We talked about acyl substitution before. Remember, we're looking for a carbonyl carbon that is bonded to something that is not carbon and not hydrogen. So there's a carbonyl carbon bonded to something that's not carbon, not hydrogen. the thing that's not carbon, not hydrogen, is going to break off, and the nucleophile will take its place. So this thing's going away as the leaving group. And the star and the dot have hooked up. Notice the OR group on the dot, he's gone. The other product of this reaction is going to be the RO minus, the alkoxide that functioned as the leaving group. The equilibrium constant for this reaction is also pretty small because esters are not very reactive. We talked about the order of reactivity, and we saw that esters, they're low down on the reactivity ladder. So this equilibrium constant is also less than 1. This first equilibrium constant was puny. This one is also puny as well. But now what we see is going to be the why we need at least 2 alpha protons here, because this guy still has an alpha proton on it. It is now bis alpha. It is an alpha proton that is sandwiched in between 2 carbonyls. So this guy here, he started life with 3 protons. He lost 1 in the enolization step. And so there's still 2 there. And now that proton is sandwiched in between 2 carbonyls. It's quite acidic. That's a powerful base. So these 2 guys get together. And what this RO minus does is it deprotonates the bis alpha position. There's my star, there's my dot. It deprotonates the bis alpha position because that's the most acidic type of enolizable proton. But this reaction, this has a whopping equilibrium constant. So the pKa of this is 10, the pKa of this is about 17. The equilibrium constant for this reaction is about 10 to the 7. Oh, that's huge. And so now we see why the ester starting material of the Claisen has to have at least 2 alpha protons on it. Because this step, bad equilibrium constant. This step, bad equilibrium constant. This step has a big equilibrium constant, and this is what provides the thermodynamic driving force for the reaction. Okay, so the Claisen is over. This is the product of the Claisen, but we normally don't want this anion. What we do now is add acid to this, and that in a separate step, and acid protonates. Sorry about that. Well, that totally screwed everything up. Okay, we'll try to carry on. We're almost finished anyway. Can you still see my board? I've totally lost control of my screen because of that call. Can you still see me? Somebody out there?
Yes, we can.
Okay, I can't hear you.
Yes, we can.
You see it, it's all good.
Okay, I don't know what happened. Add acid. And right, there's one proton there now there are 2. Okay, so that's the Claisen reaction. All right, so this is the most complicated of the enolate reactions. All right, so we just have time maybe to do 1 or 2 product predictions. And maybe we could talk more about the clays next time. All right. Okay, so let's try to draw the structure of the product here. Is it the recipe for the Claisen? It is, because I see an ester that can enolize that has at least 2 alpha protons on this bis alpha position, and then I see a second ester. So there's my star, there's my dot. I'm going to hook up the star and the dot. Notice the base ethoxide in this first step matches the esteratic portions of all of these esters. So that's another big clue that you're dealing with the Claisen. I'm hooking up my star and my dot. The esteratic portion of on the dot, he's gone. But it's all important to remember. You know, we just went through the scheme of the reactions. It's all important to remember that at the end of the Claisen step, you get a dot, dot minus on the star. And step 2 is there to put the proton back on. So this is what we get at the end of step 1. At the end of step 2, protonate the dot, dot minus on the star. And now that is our final product. Okay, so it's time to wrap up. Any questions about anything? Because I have to go to my next Zoom. All right, well, I guess if there are no questions, I'll just wish you a good day and I'll see you down the road. Stop video.